what we're looking at is this polynomial function happens to be a quadratic. The first question, will it reach 64 feet? Well, no it won't, because the maximum occurs right here at the point 1.5, 42. No. The max height of the ball is 42 feet. Now, part B kind of ties in what we're doing now. When is the ball at least 30 feet in the air? So what we're going to do is we're going to take our equation, and we want to know when this equation, which represents the height of the ball, is at least. Which inequality would we use for at least? Greater than or equal to 30. Okay, and we're going to solve this polynomial inequality. Now, we're going to use our technology. So the easiest way to use our technology to do this is take this graph and shift this down to the x-axis. How do we shift this down to the x-axis? Subtract 30. So we're causing a transformation on this graph so that it makes it a little easier for us to investigate. Because now what we're looking at is the zeros. So we're going to see if we can find those zeros, and then we're going to look at this part and see if that helps us to answer the question.
Why didn't it go down the way?
0.63, 2.36.
Because I have the same equation in, but it doesn't go down. Oh, I just like actually.
What do you mean?
Like I put in that equation, you know.
This?
But then my maximum isn't at the x-axis.
Everything above the x-axis is the answer.
I'll tell you that way.
Okay, so when we cause this shift, when we bring it down, our x-axis is kind of right here now, and we want to know where it's greater than, so we're investigating this part. And so how can I write that? It goes from
0.63.
0.63 4 to 2.366 seconds. So between 0.634 and 2.366 seconds is where the ball is above 30 feet in the air. Or at least, not above, at least 30 feet in the air. Make sense?
Yes.
Cool. Okay, let's look at one more with projectile motion. And they gave you the general form here. This is the general form. Well, G is talking about gravity, right? V naught is talking about initial velocity. A lot of times they use H. They used S naught in this one for the initial height. So if this problem is in terms, if our unit is feet, the effective gravity with the feet is the 32 feet per second. So when we multiply that by the -1/2, that's where that -16 always comes from. Did you know that? Okay. So, and then the initial velocity, and then the initial height. Now for our unit, if we're dealing with metric and we're doing gravity in terms of meters per second, does anybody know what the pull of gravity is? 9.8. So when we take half of that, that's where that -4.9 comes from. Oh, that should be squared. All right, so for this problem, I think it's in terms of feet, right? So we're going to be living in this world for this problem. So our projectile is fired straight upward from ground level. So what's our initial height off the ground? 0. With an initial velocity of 128 feet per second. So our equation is negative 16 t squared plus 128t plus 0. But we don't need that. And it wants to know when will it be back at ground level. So what height represents ground level? 0. Now, you could use your technology. This factors very simply, though, also. So go either way. I don't care. Okay. We get either t equals 0 or 8, right? So if I'm thinking about this ball and the height with respect to time, and I'm thinking reasonable domain. Does the height below ground exist even though the function would keep going? No. So the reasonable domain for this function is from 0 to 8. From 0 seconds to 8 seconds. Because time before 0 seconds makes no sense. And time after 8 seconds wouldn't actually apply, because if it's the ground at 8 seconds, then it's not going anywhere. Okay, so here's my reasonable domain. Now, part B. When will the height be less than 128 feet? So what would we do with our equation? Less than it's obviously less than 128. Now what would I do with that 128? Subtract it. Okay. Now when I start to investigate this on my calculator, I will only look within this reasonable domain. Any part of the graph outside of that reasonable domain wouldn't make any sense. Very good.
I just forgot. 6.82.
You got your zeros? Show me how you found the zero. So it goes from 0 to 1.172. And then again from
Yeah, that's it.
these are the time intervals over which that projectile will be less than 128 feet. From 0 to 1.172 seconds, and then again from 6.828 seconds to 8 seconds.
Is there a coincidence that 6,
It is.
2, 8, and 1,
Well-
7, 2 add up to
Exactly 8. The two numbers add up to be exactly 8.
It's always going to be symmetric. Oh, it is kind of a coincidence. If we started off with any type of initial height at all, it would mess that up. But because the initial height was 0, that's the reason why that works.
So if the height's 0, will that always work?
It's a good question. We could investigate.
It's good.
No, it's not.
All right. I didn't have a chance to do the rabbit problem last period. Let's do the silo, and then if we have a chance, we'll come back to the rabbits.
Or we can do it homework.
Yes, please.
Yeah.
All right. Here's a silo. Here's a picture of a silo, in case you don't know what a silo is. This silo is used to store grain. It's a cylinder with a hemisphere on top. It says the total volume of the silo is 15,000 cubic feet. And they tell us that the cylindrical part of the silo is 30 feet tall. They ask us what the radius of the silo is to 3 decimal places. So if it can contain this much, is it at the volume?
Yeah.
All right, so we know the volume. Well, let's think about how we find volume of a cylinder with a hemisphere on top. A hemisphere is half a sphere, right? Hemi means half. The volume of a sphere is 4/3 pi r cubed. We did that in warm-ups, didn't we? So this would be 2/3 pi r cubed. All right, so there's the top part of my silo. Now, the rest of the silo is just a cylinder, so it's pi r squared h.
R squared. Square.
Thank you. And at most, it can hold that much. We want to assume it's exactly equal to 15,000 for this problem because we're trying to see what the radius is. So we're going to go with that maximum amount. So this kind of bridges what we did yesterday with what we're doing today. But we can still solve it. There's one more number they gave me. They actually gave me the height of the cylinder. So instead of having h in there, I can put 30. So let's see if you can solve this. Now, before you begin though, would a negative radius make any sense? Okay. All right. Good. Just punch the pi button in. The pi button is the blue button and then the hat key that's above the division bar.
Oh my.
Are we supposed to read?
Yes, sir. Yes, sir. We're going to cause that shift.
Oh, it's really good.
showing that the radius is approximately, I guess I should use approximately here, 11.281 feet.
Yes.
All right, we will let that be our last example of the way. Your homework is on the back of the worksheet from last night. Now, the first part of your homework investigates some problems that are a little bit different. Does every polynomial function have to have zeros?
No.
No. Some functions exist totally above the x-axis or completely below the x-axis. And some of the homework investigates that. Take a look at that, think about what that would do. We'll talk about it tomorrow. And then there's some word problems for you to set up and solve.